In this video, we're going to talk about implicit differentiation. First, we need to talk about the difference between explicit and implicit forms of equations. Most of your math life, at least from Algebra 1 forward, you've been dealing with explicit forms. That is where you have something that looks like this, where it's y equals something in terms of x. That's always explicit form. It explicitly tells you that I have this function with an output y in terms of input x, blah, blah, blah. But there are different types of equations. I'm sure you've seen them already, but maybe you didn't know that they were called implicit. So that's when it's something that looks like this, where I have x and y usually together on one side of the equation that's not easily written in terms of y. This equation we can just divide by x and give us 1 over x, and I can actually take the derivative of that using rules that we already know. But this video is going to talk about differentiation of implicit forms that aren't so easily turned into y equals something. Next thing I want to touch on is the rules about differentiating with respect to x. And if I look at this first example here, I have the differentiated function of x cubed with d over dx. So this bottom denominator variable here, dx, that means that I want to differentiate in terms of x. So I have x cubed in my function here, which means that I can just apply the simple power rule to find the derivative. But as I move down the line here, I'm still differentiating in terms of d over dx, so in respect to x, but my variable of my function is in terms of y. So those two variables don't agree with one another. So that means I'm going to use the chain rule. So I'm going to substitute u in for y, and the chain rule tells me that I just take the derivative of u to the third like I would, so 3y squared because u equals y, and then I have to multiply it by the derivative of what u actually is, which is y. So in terms of x, that's dy over dx. And that's going to be a common thread here when we differentiate implicitly. And so this next example, keeping with d over dx, differentiating with respect to x, I'm going to do something here. So I have addition. I can take the derivative in respects to x because that's the same variable. That's just going to give me 1. Then I'm going to need the chain rule for this 3y. Much like I did up here, u is going to be y, so that's the derivative of 3u is just 3 times the derivative of whatever u is, which is y, so that's dy over dx. Sensing a pattern? So our last example here is d over dx of x times y squared. So I'm going to use the product rule here, but I'm going to have to take into account that I need the derivative of y squared. And that's where it comes into play here. So remember, the product rule tells you to take this first thing and multiply it by the derivative of the second thing, but because it's in terms of x, it's going to be 2y times dy over dx. So I'm going to end up with that as my derivative. So notice that when I have something that is implicit, meaning x and y within the same function, I always end up with a dy over dx somewhere, especially when I'm differentiating with respect to x. So here we have 4 basic steps for implicit differentiation. So we're going to walk through some examples of that, but these are 4 things to keep in mind. First is to differentiate both sides with respect to x, much like we did in the last slide, and then collect everything with a dy over dx onto one side, move everything else to the other, and then factor that dy over dx out, and then divide the both sides by that thing that it's being factored by, and then you'll have dy over dx by itself, which is the derivative of an implicit equation. So here's our first example. Let's find dy over dx of this implicit equation here. So the reason I'm going to use implicit differentiation is because I can't just solve for y and have it equal to something to x on the other side. It doesn't work quite so easily. So we're going to differentiate both sides of the equation with respect to x. First thing that I like to do is apply dy over dx to both sides, and that'll help me kind of break this thing apart, especially because I'm just going to add and subtract each term, so I don't necessarily need a product or quotient rule here. So let's see what we get. The next thing that I'm going to do in this case is substitute u in for y so that I can use the chain rule here. So that makes every y into a u, and then I can just take the derivative of negative x squared and negative 4, which just becomes negative 2x and 0 on this side because they're in respect to x, so I don't have to do anything special there. So let's take the derivative of these guys and see what we get. Alright, so what I'm going to do is use the chain rule on all of these things with a u in it. So u cubed becomes 3u squared times dy over dx using the chain rule. Same deal here, 2u times dy over dx. The u goes away in this situation, so it's minus 5 times dy over dx, and I still have that negative 2x equals 0. So I replace every u with a y, so that's what's in green here. I isolate the dy over dx, I factor out the 3y squared plus 2y minus 5. I move that 2x over by adding it, and so I divide this 2x side by this green piece here, and I end up with my derivative of this entire function. My dy over dx is equal to 2x over 3y squared plus 2y minus 5. So up next, let's talk about graphs and differentiable functions. So let's have a look at these three examples here, a, b, and c. And if possible, let's see if we can represent y as a differentiable function of x. First up, we have what we assume is an equation of a circle, right? X squared plus y squared, but it equals 0. So this is just a point in space. So as a single point, it doesn't define y as a differentiable function of x. So that's a no-go. Next up, we have another circle, x squared plus y squared, but it's equal to 1, so it's more than just a point. And I could split that up into two different equations for y, so that's the square root of 1 minus x squared and the negative square root of 1 minus x squared. So that makes the top of the circle and the bottom of the circle. And I can trace many different tangent lines along this circle, except at these 2 points, negative 1 comma 0 and 1 comma 0. So this entire function is differentiable in terms of x, except for at these 2 points. And then for c, we have a parabola, so x plus y squared equals 1. And just like in the last example, I can draw a ton of tangent lines all along this curve, except for at this point, 1 comma 0. So it's like this last situation here, where it's going to be differentiable with respect to x, except at this point 1 comma 0. So something to note is that you may have a function that has either a part or all of it that is differentiable, or none of it that's differentiable in terms of x. You just have to be careful how you restrict those things to differentiate. So for our next example that we're going to work out, we're going to determine the slope of the tangent line to this graph of this ellipse here, this x squared plus 4y squared equals 4 at this point. So all we're looking for is the slope of the tangent line, not the equation of the line. And I'm actually going to differentiate this thing using implicit differentiation. So the first thing I'm going to do is apply my dy over dx to both sides, and I'm looking for the derivative in respect to x. So this part's just fine. I get 2x there. And then remember, I need the chain rule here, so I take the derivative of this as I normally would if it was in terms of y. So that's going to be 8y, and then I have to multiply it by the derivative of dy over dx. And of course, the derivative of a constant is going to be 0. So I move this 2x over, I divide by 8y, and I find that dy over dx is equal to the simplified version of this as negative x over 4y. So my job isn't done. I need to plug in this rad 2 for x and this negative 1 over rad 2 for y and see what I get for the slope. So once I plug all those things in and I simplify, I get the slope of the tangent line at this point is 1/2. Now let's work through a similar problem where we're going to determine the slope of the graph of this function, which actually produces a lemniscate at this point 3, 1. So we're looking for the slope of this tangent line right here. So let's walk through the first couple steps together, and by no means is this finished where it is, but the first thing that I did here is I saw that I'm probably going to want a chain rule first thing because I see x squared plus y squared all to the power of 2, so I'm just going to sub that in right away with a u. So x squared plus y squared is now my u, and I will use the chain rule to apply that to this thing. So that's just going to be 2 bring it down to the 3, so that's 6u times whatever the derivative of u is, which I'll do in the next step. And then I can just apply my dy over dx to 100 xy and use my product rule there, keeping in mind that y, or the derivative of y, is just going to be this dy over dx. So going back to this 6u times u prime here, or the derivative of u, I have replaced the u with my x squared plus y squared, which is easy enough to do here. That's just a simple substitution. But the derivative of u itself, so I can take the derivative in terms of x, that's easy, that's 2x, and then it's going to be plus 2y times dy over dx, so that's a chain rule within a chain rule itself. So the remaining steps to be done here before I plug in my 3, 1 to find the slope is really just to distribute as best as I can and get that dy over dx by itself. All right, let me walk you through some algebraic stuff here. I kept this right side of the equation the same until I needed to move that thing with the dy over dx over to the left-hand side, but we'll get to that in just a moment. So once I plugged in my u values here and I have everything out, I pulled out the 2 from this, so that allowed me to multiply the 6 times the 2 to put the 12 out here and have that x squared plus y squared times the quantity of x plus y times dy over dx. And then I took this quantity here that I've bracketed in red and I distributed it to each piece in this next parenthesis. So all I did was distribute, and that allowed me to take this quantity here and move it over to the right-hand side using subtraction, and allowed me to keep this with the dy over dx on the left-hand side, along with moving this over, this 100x times dy over dx, moving that over with subtraction. So what I end up with is a not so pretty derivative, but most derivatives actually aren't that pretty. So my numerator is this piece over here without any dy over dx in it. So that's 100y minus 12x times the quantity of x squared plus y squared, which is up here. And then the 12y times the quantity of x squared plus y squared minus 100x is going to be my denominator here. So what I'm going to do with all of this is plug in 3 for x and 1 for y and see what my slope will finally be. So what we do from here is we take our equation, which does not have to be pretty, and we plug in 3 for x and 1 for y, and you simplify it all down, and the slope of this tangent line right here at 3, 1 is going to be 13 over 9. All right, let's do another example, much like the others, where we're going to find the tangent line this time, though, to the graph of this kappa curve, so x squared times the quantity, x squared plus y squared, all equal to y squared at this lovely point here. An option you always have, and what I'm going to do in this example, is distribute this x squared to each of the terms on the inside of the parenthesis, and I'm going to subtract the y squared so I have everything equal to 0. So really, I'm just going to need the chain rule because I have got a couple y's here, and the product rule, which will be a little bit easier than having a double chain rule. Or so I think. So that allows me to take my first line and my derivative here. So x to the 4th becomes 4x cubed, and then I'm going to use the product rule here. So that's x squared times 2y times dy over dx plus y squared times 2x, which is the derivative of that guy. And then I'm going to subtract the derivative here, which is going to be minus 2y times dy over dx, which is always equal to 0 because the derivative of a constant is 0. And so I move all the things with dy over dx to the left side. I move everything else over with subtraction. I factor it out. I'm able to actually factor out a negative 2x on the top and the negative 2y in the bottom just to simplify things. So here's my derivative in technically simplest form. And now all I need to do is plug in rad 2 over 2 for x and rad 2 over 2 for y and see what my slope of this tangent line is. So once I plug that into this form, I end up with 3 as the slope of the tangent line, but remember we need to actually find the equation for the tangent line, so I'm going to use that and plug it in and see what that is going to be. Now using that slope of 3, I'm just going to plug it into this general form here, and I can have this equation here, or y equals 3x minus the square root of 2. So that is the equation of that tangent line at that point. So the last example we're going to work through is actually finding the second derivative implicitly. So let's say I have this circle equation, x squared plus y squared equals 25. Let's find this second derivative in respect to x. First thing I do is find the first derivative in order to find the second. So I take the derivative here. It's pretty simple. Going to be 2x plus 2y times dy over dx equals 0. I move the 2x over by subtraction, divide by 2y, so I get negative 2x over 2y, which can be simplified as negative x over y. So now I'm going to take the derivative of this to end up with my second derivative. So how I make this a little easier is I rewrite this as negative 1 times the quantity of x over y. So I'll use the quotient rule for that and just keep the negative 1 on the outside. So when I take the quotient rule here, I have y times 1 minus x times dy over dx, because that's the derivative of y. And we know that dy over dx is the same as this thing right here. So I'm going to substitute in negative x over y. And simplify that there, and that's all over y squared. So here's what I have. I simplify it down. I end up with negative 1 times the quantity of y squared plus x squared, which is actually 25. So I'm going to substitute that in with a 25 because I can. And that's all over y cubed because that y and that y squared turn into y cubed. And so I end up with my second derivative being negative 25 over y cubed. And that's going to do it for this video. Thanks for watching.